Good afternoon, everyone. Welcome back. Today, I'm going to demonstrate the KKS OpenCL module in MicroSim package. So, this was this work was part of my doctoral thesis, and my supervisor during my PhD is Professor Gandham Kumar, who is here with us. Let's directly go to the details of the model. So, as it's a phase field package. Probably you might hear the phase field equations now and then. So as a overview, I quickly glance through certain equations which may be repetitive in all of the talks, and the equations which are essential for this model, I will stay and emphasize more. So as we know, the phase field model here it comes with a description of the Gibbs free energy, which is we take as a Gibbs energy of the system, which has a contributions of the bulk and the interfacial energies, and the free energy is minimized, and depending upon the kind of problem we are looking and the phase field parameters we are looking, whether it's a conserved variable or non-conserved variable. So we have both the Cahn-Hilliard equation and the Allen-Cahn equation. So coming to the case of solidification which we are going to deal here. So in this model, we are describing the phase field with a value of 1 for the solid phase and 0 in the liquid phase, and altogether the interface region is represented with a value within the 0 and 1. So here you can see a schematic which represents a diffuse interface approach, unlike the sharp interface approach where the interface profile is a very sharp in the interface. So coming to the free energy of the system. So as I mentioned here, the contributions of the bulk and interfacial regions. So this how we are going to get the free energy of the system. So here I'm taking this bulk energy and it has a contribution from the real Gibbs energy of the system and the phase field model concepts where the double well comes up. So that energy is here, and so the free energy of the system is interpolated or through the interpolation function called h of phi, so which extends between the solid and liquid phase. And similarly, the double well potential this is a function which shows the minima for the two phases at 0 and 1, and the function is of this form. So altogether the free energy is given in this form. And so as a just for a representation, so here is the double well function profile where it has minimum with 0 and 1, and the interpolation function which extends through continuously from 0 to 1. And coming to the model, the evolution equation in the KKS model, it is given over here where the phase field evolution is given and the driving force given in the terms of the driving force for the solidification and all other contributions to the phase field model parameters. So the essential thing in this model is that the composition in the interfaces is taken as like a mixture rule or extended through the interpolation function, and the interface at the interface the chemical potential equilibrium condition is satisfied, and the parameters which are going into the model are evaluated accordingly. I will explain. So m phi, epsilon phi, w, these are the phase field model parameters which can be correlated to the material parameters, and the free energy Fs, Fl are the solid free energy, liquid free energy, and Cs, Cl are the compositions. So these are the equilibrium compositions which are attained from the simultaneous solution of these two equations. So we will employing a Newton-Raphson method to solve these equations, and then the composition evolution equation in the system we can study it through this diffusion equation where it is coupled to the phase field equation through the phi, and we can see here again the contributions from the solid and the liquid which are interpolated through h of phi. So this interpolation is done for the mobilities. So through the mobilities the final equation looks like this. So one of the problem in the phase field model is solid trapping at the interface. In other words, it's a chemical potential jump. During the solidification at low undercoolings or else low growth velocities, when we bring the solution of this phase field equation asymptotic limits into one-dimensional way, so there is a mismatch on the compositions on liquid side and solid side. In order to compensate this problem, so there is a mathematical term is added, which is called anti-trapping current, which is a flux from solid to liquid, so which is essentially normal to the interface given by this function. So these implementations are already available in the model in the microsim package. We have the flags whether we would like to enable this anti-trapping current, or whether you want to simulate the solution with the implementing both the solid and liquid diffusivity. So all these possibilities are there. And the next one is the anisotropy in the phase field. As we have mentioned, so ideal the previous model, the equation above which represents alone solves for isotropic case. If you want to introduce anisotropy in the system, so we have to introduce, we can introduce it through the mobility parameter and epsilon parameter, the gradient energy coefficient. Here we are taking the gradient energy coefficient. And one more thing I would like to emphasize, the anisotropy why we would like to introduce is, we know because of the basic structure of the material, the growth is preferred in the certain directions. So because of which the anisotropy develops in the system. So one is such example is the dendrites growing with 4-fold symmetry. Other is the dendrites growing with a 6-fold symmetry. So here I am showing the example where the 4-fold anisotropy is implemented. So the basic cost function can represent this function. So this can be converted into the phase field variable in terms of the phase field variables. The phi x, which is nothing but the gradients in the phase field, which are essentially non-zero at the interface, which decides the anisotropy in the function. So this is also implemented into the model. And the next is, as we mentioning previously, the imposition of temperature gradient. We are going to introduce a one-dimensional temperature gradient. So that is introduced through this equation, where the T init represents the initial temperature at x is equal to 0 and t is equal to 0. For example, if you want to keep the temperature at a distance of x is equal to some finite value, so the facility is also provided where you can the scheme is accounted in this x. Here for example, you want to keep the liquid temperature at the solid liquid interface over here. Then you can choose such a way that you can give the distance. What is the distance from this domain boundary at the start of the boundary to the solid liquid interface, which we are going to initialize, and you can provide that x over there, and you can carry out the simulations. So this is very helpful in carrying out the directional solidification simulations, which can be taken as the application for welding simulations or additive manufacturing simulations. The one other case is isothermal simulations, where you have a uniform liquid with a constant temperature, where the seed grows into the supersaturated liquid. You can create a nuclei at any position of your interest, as shown over here. So the similar schemes are available. And as I was mentioning, the parameters in the phase field model are related to the material parameters. So here we can see the interface energy and the interface thickness are extracted from the phase field evolution equations, which has this form of function, from which you can get the values for the height of the double well potential, which you are going to use, and also gradient energy coefficient you are going to use. So such a way that you can use these values in the model. And also the phase field mobility, which drives the interface, also is taken with this form. So and so these functions are already available inside the solver. So the user only has to give the material parameter input, and as you mentioned, the free parameters interface width and the grid size can be taken into the solver. So this is essentially a breakdown of certain parameters which are available in models, so material parameters and model parameters and numerical parameters. The material parameters are like Gibbs energy, diffusivity, anisotropy, which includes the strength of anisotropy and what kind of anisotropy. And the model parameters interface with the double Bell potential height, gradient energy coefficient. So certain for this model, certain model parameters are already inbuilt in the mod inside the solver. So user need not worry about that. And the numerical parameters are the what is the grid size you are going to use and a time step and other things are number of time step and saving time, so other parameters which are going to into the model for which you are going to get the solution. So one more thing I would like to emphasize is that so this model will take the Gibbs energy descriptions which are in the form of Redlis crystal polynomials which are developed through the CALFAD method. So this information of the RK parameters is placed stored in the form of databases called the TDB files, and we can read the TDB file directly in our simulations where we will feed the only the name of the TDB file, and the PyCalFAT based the Python interpreter is there which reads the TDB file and generates the Gibbs energy of the required phases. For example, here it is solid and liquid, and you have to provide the input of what are the elements we are going to use and what are the phase, which solid phase, for example, if it is FCC or BCC, such kind of information we can provide in the input file itself. So it will generate the Gibbs energy functions in the solver, and the solver will run based upon that in Gibbs energy functions. And so just to give a brief idea, so the Gibbs energy which we are going to use have a contributions of reference state and ideal mixing and non-ideal mixing. There will be other terms which are physical terms, for example, magnetism and so on. So which are I am not considering at this point of time, which problem of our interest, because of certification is a problem of interest where the magnetism may not exist. Mostly it won't exist. And so the TDB will have the information about the Gibbs energy contribution from non-ideal interactions. So this is called excess Gibbs energy, so which are modeled through this expression. So this is example for binary. So this extension or the form can be extended into multi-components also. Here, so the LAB is the RK parameter, which is actually being modeled, where the model parameter A, B are developed through the CALFAT method. So coming to the after this information about this, just I will like to give a brief introduction about the implementation. So here we are going to use finite difference method as Professor Abik is mentioning, where different kinds of methods are involved, finite volume, FDM and so on. So we are going to use FDM, and we used Euler explicit scheme for time and space because of the parallelizability of this method, and we used the central difference method for gradients, and also we used isotropic stencils. Here I am showing the examples of 2D case, but the solver is under development where the 3D code is also we can use where isotropic stencils and the similar implementation is also achieved. So in order to get the longer simulation domains, and owing to the computational cost or expensive nature of the phase field models, the moving frame approach is model. So it is also available in this model where you can shift the domain if you are running out of the limited domain size you are available inside the simulation domain. So with that, I would like to take one more indication that this model is implemented on a GPU. This is so as we know, the GPU implementation is basically available for the in the form of OpenCL and NVIDIA. So unlike NVIDIA, OpenCL is much very cross-platform compatible. So here we are using OpenCL 1.2, which can run across all the CPUs, all the GPUs, and even including FPGAs, which are latest hardware. And the advantage of OpenCL is, so it is so much cross-platform compatible that I would able to run a test case even in my virtual box inside the any guest OS. So that is advantage we are going to have. So here is a basic implementation of the OpenCL, where you have the host and the device, which is nothing but the graphics card or the CPU which we are going to use. So basically the scheme we are going to adopt here is we offload entire the domain onto the GPU, and then we transfer the data, and we offload the entire data to the GPU. How it is being done is once we allocate the memory on the CPU, the equal amount of the memory is allocated on the GPU, and there is a physical transfer of the data from CPU to GPU, and the memory inside the GPU is left to the GPU so that it will handle according to the device capabilities. So it has a different sections where the global memory, which can be visible for all the solvers, all the work items which are inside it, and local memory, which is visible for a group of work items, and the private memory, which is visible only for the work item. So this group of items are called compute units and so on. So this is nomenclature of OpenCL. And the coding method involves in first we have to get the device which we would like to run, and the memory allocation, and then context creation is where we are going to run, whether we are going to run CPU or GPU, whether we want to run multiple CPUs or multiple GPUs. So those kinds of information is handled over here, and the command queues is where actual our solver functions present. These are kernels which are called which will run on the device are being enqueued through the command queues. So the device code is nothing but the kernel code, the solvers which we write present over in the form of kernels. So with this, I would like to thank you for your attention. We will go for the demonstration. I would like to take any questions here if anyone has, probably before going to the demonstration.
Mohan, Gerald here.
Yeah.
I just wanted to know, you showed a representation for a four-fold system. So the provisions for six-fold are present. For example, if I want to do a six-fold thing, they are present in the simulator.
Yeah, this simulator right now it is not present, but we have plans to incorporate it. And
okay.
So the basic idea of microsim is we can choose all the parameters, all the features across the different models wherever it is possible. So this is which can be possible for six-fold symmetry, which can be accommodated into this model. So we will implement it in future release.
Okay.
I'm going to open my microsim profile here. So, but before, as I will explain accordingly through some of the in files and also some of the features through the simulator, because I would like to emphasize certain features which are available. So we'll go with a new in file. One more thing I would like to emphasize is before going to the new file, we should know that what kind of system we are going to use. For example, as we are using the real thermodynamic database, so the information whether it's FCC or BCC, and the naming should be taken conveniently, which is common across the TDBs, so that there won't be any errors thrown up later on when we are generating the Gibbs energy. So for that, we will generate the input file over here. So we, as usual, we'll start with two-dimensional domain. First, I will run one simulation with generating the in file. Later, I will import the existing solver for 1 second case. So I will give some small size 256 by 256, and we are going to do only a two-dimensional simulation. So we see the third dimension is already disabled, and we are going for the discretization. As I am mentioning, so the delta x or delta t are non-dimensional values we are going to take. So here I'm going to take certain value 40 or 40, and here I'm going to keep it as 1, and this value is 320. So the delta x, delta y, you can take anything based upon how you are going to non-dimensionalize your scaling values, and delta t accordingly you can take, so that the stability of the equations also achieved while solving the evolution equations. And the number of phases here are 2. So I would like to emphasize here that we would like to make sure that the phase names are appropriate which are present in the TDB. So I am using here FCC as my first phase, which is the evolution solid phase which evolves through the liquid, and I'm saving. And the number of components are 2. So the solver is solves for binary Li right now, and I'm going to give the names NB, which is one of my solute in nickel matrix. So this is the example which I am going to show is a nickel niobium alloy system. And going to the next slide, so the total number of time steps, so I'll retain to some 1000 steps. So this N smooth is the smoothing of the phase field profile before actual implementation of all the features, the anisotropy or other driving forces. So which will, so I will use some 10 time steps to smoothen the phase field profile. I would like to save it every 100 time step, and as we are going to start a new simulation, the key is left as 0. So we can see as such that these two fields are disabled. And coming to the next, so here as we mentioned the phase FCC phase, so it is automatically enabled. So I'm going to use the diagonal matrix. So I am giving a diffusion coefficient which is in the order of 10 power of minus 12, which is a typical order for the diffusivity in the solid. You can get these values exact from the diffusion database like TDB files. There exist DDB files. The availability of this information is very rare, but some of the commercial softwares or some of the open literature where the numerical values are posted, we can pick the actual value related to your Li and give the information over here. So this elastic constants, which is kept common across the solvers, I'm going to fill it as of now. This is not, these two elasticities parameters are not related to this solver. And so this infile is generated keeping view of all the solvers across. So certain features we have to explicitly exclude. So here I can't use the same as previous because I'm going to give the different value for the diffusivity, and I'm going to give a diffusivity of 4.3 E minus 9. So this is, I'm guessing with my approximation, this is going to be more or less equal to the real system. The exact value can be always attained through different resources, through literature or the databases. The gamma is a solid liquid interface, so which I'm going to give as a some 3.7 value. So these are values also material parameters. So gamma is a solid liquid interface also, which is a real value for the system. So which you can get experimentally is very difficult to get. So you can use the simulation tools like molecular dynamics to get these values. So as I'm giving all the values, material parameters as a dimensional values which are in the SI system, I'm going to give the gas constant and the molar volume also in the real units. That means the dimensional values. And so some of the values I'm giving in the range where the exact values are not available. So that is keep in mind. And the phase field solver which I'm going to solve has a boundary condition. We are going to use a no boundary condition, and which is same for all the directions. And also I'm going to solve for composition, and I'm going to use no boundary condition, and which is same for all the directions, which I'm going to mark with this. And so we can use the same as here, and temperature also I'm going to solve it through no boundary no flux boundary condition, that is Neumann boundary condition, and I'm going to add the same thing in all the directions. So now I'm going to add, so I'm planning to do a isothermal simulation where you keep a circular seat, and so this is done through cylinder, the two-dimensional projection of a cylinder being circular, so the dimensions can be given. So I'm going to keep the center as 128, 128, because I remember I gave the 256 as my domain size, and the radius I'll give some around 40 grid units. Let's see what is going to happen. Save, and I'm going to add next. So here option keeps, so now only we are going to get the model specific parameters here, and I'm going to select a KKS GPU OpenCL model, and going press further next. So this is a binary ALI, and which enables the number of components too. So that is by default it is filled here. So I'm going to do a isothermal solidification. I'm going to use you can use ASCII or binary format. So let's, as of now I'm going to keep ASCII, and so I'll keep track progress. Probably I would like to do it every write time step. Next is the epsilon, which is the in this case it is the interface width, which I'm going to give around some. Let me check my in file so that it won't run into errors. I'll make it a proper choice. I'm feeding certain parameters looking at my existing in file. So I'm going to give 400, and the function anisotropy I'm going to enable, and I'm going to give strength of anisotropy as 0.02. So this value also you can get it from lower length scale simulations, and the epsilon, which is a free parameter, which you can, and the epsilon, which is nothing but the interface width, free parameter, you can choose depending upon the system and the material parameters we are going to use. And here the noise is the implementation of noise is being used, especially in the dendritic simulations, to introduce the fluctuations at the solid liquid interface. So these fluctuations are range where the length scales of the fluctuations are way below the phase field capturing length scales. So we are physically introducing these fluctuations through the manual introduction of price, which is nothing but a random number generator. So which I'm going to enable. So I'm going to add some. This is the amplitude of the noise we are going to use. So we have to make sure this amplitudes won't go beyond certain value, maybe some 5% or maximum 5%, so that your solid liquid interface should not distort physically because of the noise. The phase selection or phase evolution, the microstructural feature evolution should happen through the physics of the problem, not should be influenced by the external parameters like the random numbers which are introduced for the noise. And similarly, as we smoothen the profile, here also we would like to spend some time, some time steps before introducing the noise. So I'm going to keep it as 100 time steps where the phase field profiles smoothens out and evolves. Later we will introduce the noise, and then what we will use is, in the next case, is the temperature, as we've seen. So we are going to use the isothermal case. So I'm going to use this value. Actually, I should know the liquidus temperature for this alloy. For this is 1696, and I'm going to use the 1690 as a temperature, which is going to be undercooled for 4 Kelvin. So this is the kind of simulation we are going to use. If you am going to introduce temperature gradient, this feature will enable. So that I will import and let you know, show how it is going to happen. And this anti-trapping current, which I have mentioned previously, this is the to avoid the numerical solute trapping or artificial solute trapping happening at during the solidification, which is not physical at lower velocities. So I'm going to enable it so that the anti-trapping current is introduced in the solver. And as I told, so the device selection right now it is manual in the OpenCL implementation, especially in our solver. And so it is basically a runtime compilation is going to happen during the execution of the code, so which requires to know what kind of platform it is looking at. So each platform runs differently. So if there are multiple platforms, you better to know what platform you want to run. Whether and a basic desktop where you have both graphics card and CPU. So you can install OpenCL for both drivers for CPU and GPU. So, and if you are going to run on a cluster or a dedicated server where the computing GPU cards are available, so mostly there you will get only one platform of the GPU, which by default it will be 0. Here also I'm having only one platform, that is CPU my case, and the device ID is 0. I mean, it indicates what kind what device number you are going to choose. For example, nowadays the supercomputers, each node equipped with 2 or 3 graphics cards. So there you can pick the device which GPU you are going to run. So this is some time which can be communicated within the system and the cluster and the in-file generator or the scheduler. And being if you're going to run on a multiple GPUs, so the required scheme is will be implemented. So the scheme is right now we are going to use only single GPU implementation. So only one GPU, which is going to be one GPU. I gave it as a single device ID 0, and I'm going to use a TDB file named for the nickel niobium system. Here I'm going to show the name of the TDB file. So each the PyCalFat based Python interpreter will read this TDB file, so which we will look in further down while running simulation into the details. So that will be appropriate, I feel. So we can spend some time on it. And then, so here are the parameters, compositions which we are going to use. So the equilibrium compositions are the equilibrium which we are going to study, and the filling composition are which you are going to have the composition initial profile. So basically I have supersaturated liquid. Correspondingly, I will give the solid and liquid composition over here. So we remember that we give phase 0, 0th phase, the first phase as solid. So the phase indication over here which represents the 0 0, the equilibrium values for 0 0, that means solid solid, 0 1 liquid solid, and solid liquid solid solid the other way. So all the options are available. Certain cases the values may be similar, so you can fill the values accordingly. So I'm going to so these values are actual real Ally parameters. So I am going to fill the appropriate values, and so these are the equilibrium values in the system, which you can get it by reading the TDB file and providing the appropriate input temperature or Ally composition, and get these values from the system. So I just enter. So the equilibrium values are the isothermal simulation I which we are going to do. So those values are over given here, and similarly for both solid and liquid. So why I'm emphasizing on giving the exact values? So the solvers sometimes diverge depending upon the material system. So we better stick to actual values where we can provide a close guess for the solver where the Newton-Raphson implementation was available to solve the equilibrium composition. And so we can implement different schemes instead of going for a Newton-Raphson method. So right now we will look at those options later on, and so I'm going to use the rotation matrix where I'm going to use only 0. I'm going to introduce any rotation. So with this, it will tell us to generate the in files. So I will run one input file and filling run one. So I'll generate files. I'll try to generate files in my solver right now. I'll tell you why, especially this solver. Sometimes the possibility to run the execution of the code may become difficult if the runtime files are not available. So that we can check. So output I'm going to use as output run one, and let's start running. And while running, we can look into what is going behind. So we can see. So it shows it identified there is only one iDevice in the one platform. So so that is being selected, and I selected the CPU, and accordingly compilation, the runtime compilation happened, and the kernel optimization happened depending upon the compiler using, and then you are start running the simulation. So it may be slow, and let's see. Okay, it has generated one time step at 100. Let's see a preview in the para view, and it is over here. Yes, apply, and good. We have the naming also conveniently, where you can see the FCC is being named, and where the center circle seed you can see, which kind of already evolved. We can see that the initial profile we can see over here. Sorry for that changes. So we'll open all the files, apply, and so you can see the initial circular seed started evolving. So yeah, it's only happened at 2 time step. You can see the slight growth process which is going to happen. So let it run properly. So during this process, I skipped one stage. Sorry for that, where the in files were the Gibbs energies are generated. So that I would like to show. CDKKS OpenCL. Here you can see the TDB is available here, so you can keep the name of your convenient, but it should be consistent across. So we have a ready-made script where it can show how to execute this along with the execution of the Python script. So if you are running for a new Ally, it is always advised to run through this command, or generate the Gibbs energy descriptions manually. If you are repeating for the same Ally, the Gibbs energies will be stored. So the compiled file will have the descriptions of that Ally system. So you can see the Python, and you can use the name of the Gibbs energy. So the Gibbs energy writer is the script, Python script which generates the Gibbs energies. You can give the input file as which one we give, run one as the input. So you can see here it will start generating the Gibbs energies. So it is based on SymPy, so it will go through the reading the TDB and it identifies. So this is the niobium nickel is the system which we are going to deal, and so phases are FCC, A1 and liquid. So you remember we have given the name FCC, but actually the convention which is available inside the TDBs are FCC A1. So these are depending upon the structure factor, I mean depending the name convention based upon the structure notations previously adopted. So this is the structure name of the phase, and also so this is very essential. If you interchange the nickel and niobium or liquid and solid while doing input, so these values will be interchanged and your Gibbs energies correspondingly will change. So yeah, you may not expect what you wanted to do simulation. So this care should be taken while running this code. So and so it is, there are certain conversions which whoever interested can go through, but what is happening is, so the SymPy is generating these descriptions into a form where it can compiled in a C program. So it generates C values, so it gives the successful calculation of the partial derivatives in for the Gibbs energy in first order and second order, and you will get a message files are generated successfully. So let's see whether what is status with our simulation. So it is there at the last step, and so we can preview again. Sorry for that. Yes, and apply. So yeah, it is growing slowly. So sometimes the calculations may be tedious because you are going to use the real TDB value expressions, but you can take the you can consider these values are exact. And also this is going to we are going to introduce features where user can input a simpler polynomial instead of this complex Gibbs energy expression which involves in logarithmic terms and so on. So that alternative can be provided. So you can see the composition evolution and the phase field evolution. So it is isothermal system, and let us see. So with this I would like to close the so this has finished the run. So the you can visualize the data and you can do post process of your convenient. So which is the data is available inside the data folder and you can use. So I'm going to do a new simulation where I'll import instead of doing this, I'll import and do a temperature gradient calculation. So let me, yeah, so I'll go back. So it has flexibility to go back and edit the parameters. So I'm just going to the beginning and choosing KKS GPU OpenCL model, choose in file. I'm going to choose in file which is available over here. So I have prepared already in file, so that I am going to use this file and parameters in file. So this is good. So it tells certain parameters are missing, so which we can add. So as we proceed, and then next. So one thing, sorry about that. I'll choose a file again. Okay. What I would like to emphasize is once the display, so the phase names you can see they are imported whatever we give FCC and liquid, and the similarly the element names also imported. All the parameters are imported over here, and then next we'll add cube. That will be ideal. So we will add 0 0 0 0, and so we are going to keep a cube, and which is for extending in throughout the x direction, and with the seed radius which is equivalent to, I will keep some 50 radius which thickness, and other direction is 0. Say invalid start point. Sorry. Say next. So you can see the model, it was already loaded over here, and here you can see inside the model the simulation details are already available, and temperature gradient is enabled over here. And then you can see next will generate it with 2 and 2 generate over here. Okay, just start running this. So this is the way we are going to run. And as I was mentioning, if some let that run. If someone is wanted to run through scripts, someone is asking previously, those who wants to use the terminal for execution in bash process, so you can use. So I will show you the basic execution. You can make the solver to generate the make file. You can see it generated this file, and you can run. So as I mentioned, so we are repeating the calculations within the same solver which is compiled, so the Gibbs energies are available. Otherwise, ideally you can run the Gibbs energy descriptions, or you can use this file to run complete execution. So I'm skipping that part. So I'm going to run microsim input and input to file. I'm going to use this is the file. So before that, let us see whether what we are going to use. So this will have all the information which we can generate through the input file. So all this information is available over here, and I would like to do one thing is here. Here you can disable. So let me check whether I'm enabled a gradient here. So this is not enabled for a gradient. So let's skip this. That is good. Yeah. So I'll use the input file as such, the input file. So which has the feature enabled for the gradient, where we give the gradient information, and which is enabled through isothermal solver, isothermal disabling. So you can import the same solver. So I don't want to repeat through the GUI. So we can import it the same way, and you can execute microsim input dot in filling, and I'm going to give a name for temperature gradient as the output file name. So let's see what will happen. So it's sorry for that, something is missing. So this is basically a problem with the compiler. So this compiler for GPU is let me check again. Under development. So the uniformity across all other parameters is not available right now. In the case of GPU compiler, yeah, you see now it is compiling the reading information, and the similar things is happening. And you can see, though the simulation is running across two different values, you can see that is inside the data the basic time step is not okay, it has run. So the TG which indicates the details about the temperature gradient has given here. So if someone wants to do manual checking, you can use the always the executable available in your system, and load it with this ParaView. And I'm going to show this here how this test case is going to happen. You can see a rectangular domain where You have the phase information and the composition information and the temperature gradient information. Here you can see it's a linear temperature gradient which is fixed over here. So with this I would like to stop and take any questions in this regarding in this module.
We answered this question, but there is something about anti-trapping current. That's implementation and the issues with ignoring it.
Okay. Anti-trapping current, but what happens is the results you are going to get will have some error. They may not be realistic. You can use without anti-trapping current for some equilibrium studies where equilibration studies where you can want to see how the composition evolves at a lower in isothermal case under equilibrium. So those cases it is preferred, but you can do the simulations without anti-trapping current also by providing the diffusion coefficients both in solid and liquid. But it will have always carry some error values, so that you have to keep in mind. Otherwise, the one more thing I forgot to mention. So this solid trapping happens because we are tended to take a higher interface with values in order to scale our simulations to mimic the realistic microstructures. During this process only it will, during this process only this solid trapping happens. But otherwise you have to choose very fine grid size or interface with grid sizes which may not be suitable for doing a realistic simulation. So this is a trade-off, or it's a physical phenomena which you have to account when you're doing realistic simulations through larger interfaces.
Oh, there is another question from Harris Daniel. Is
Okay.
the temperature gradient activated in the code? Will it affect the results?
Yeah, it is activated. So I would like to mention the previous release it was not activated. So the now current development version which is available in the microsim repository at the GitHub, it has the temperature gradient implementation. So if you are going to the previous release 1.0.2, the temperature gradient for this solver is disabled. So I would like to mention, emphasize that specific to the solver.
And the same participant also has another question. Can you run us and show the results for different values of delta T, delta X and delta Y other than 320, 40? Because
Yes.
when we tried running for different values of delta T, delta X and delta Y, the code faced problems.
Yeah, I can show you those values. So as we mentioned, in the slides here we can related the material parameters. We have to always keep in this mind when we are giving the input parameters on into the model. So how we are going to scale your interfacial energy and how it is going to happen. So certain idea of these numbers will help in choosing the delta X and delta Y and the delta T. So for this model, they need not to be limited to the 1 or the below 1. They can be any number which can be scaled on any other dimensional parameter. So that is I would like to emphasize. So probably that that can be taken into account, I would say. And the repository right now has different input files where you have the different delta X, delta Y that you can use. For example, the one which we ran input.in, it has a different values. So this is running over here, right? So input.in, which we have used, it has 15 and 15, some other values. So there I gave specifically because yeah, we have to get the idea of the numbers. So that's why I choose those numbers specifically.
So just to add, the
the delta X, delta Y, delta Z are typically chosen based on the interface width that you want to have in your model. So the interface width is an input parameter. So depending on how many points you want in the interface, that will dictate the delta X and delta Y that you choose. So so that's essentially a property of the model. So you must know in that model there must be some. So as he gave the relations. So once you have the interface width given, you typically would like to have about 10 points in the interface. So that tells you the delta X and delta Y that you need to choose. And depending on the delta X, delta Y, because this is an explicit time integration, the stability arguments would dictate what delta T you can use in terms of the time step. Yeah, so that has to be sort of figured out.
Thank you, Professor Abhi, for emphasizing that fact which I missed.
So Mohan, more questions are coming now.
I'm not sure, so I cannot see. So I think this one, right? So
Yeah, I didn't see any more questions, Mohan.
So okay, and then I'll show this the temperature gradient, how it evolved through here, and let's close after that. So it started evolving. So these values sometimes these parameters, I mean, these simulations tend to take a longer time because of the complex, the non-linear nature of the equations involved. So it started evolving. Hopefully, in a bigger system, it will run and to a much nicer dendrite or cellular mesh structure. Thank you. Shall I stop my sharing now if there are no questions? What?
I don't see any more questions, Mohan.
Okay, thank you then.
Okay, so we can wait for some questions to come, and before we start off with the next one. In the schedule, we have about half an hour break between the talk of Mohan and then Shashwato. So
one more point, Abhik.
Yes.
We will take questions across all the topics, right, in these breaks, so
right,
that
right, exactly.
Some students may not have asked in a previous session, but they may think of it now.
Exactly. So if some people have questions from different topics, I mean different talks that were there today, they can just go ahead in the break. Yeah. We are there. So. So by the way, thanks Mohan for the nice description from starting from the infile and slowly going over how to get a simulation ready. The particular emphasis on getting the on how to read in the thermodynamic database file and how to utilize the PyCalFat interface. Okay, there's some echo from somewhere. Yeah, so I think that is one of the fun feature we will be adopting across all our modules. We are going to do. Right.
So Abhik, by running that GE data writer,
Right.
so we'll be able to extract the polynomials as well as the diffusivity slash mobility.
It uses the SymPy interface, so it reads it as an expression.
Okay.
In Python, and using the code generator in Python code gen library, you actually write down .c.h files use as C functions.
Okay.
So you essentially don't have to do anything. It's just that PyCalFat interface and the code gen library. That is what that code Python interface is. It just will produce .c.h files corresponding to the solid and liquid phases and all the functions that you need. And since these are symbolic expressions, you can use SymPy to compute symbolic derivatives and load them as functions also. So let's say you want double derivatives, you can load them as actually compute the symbolic derivatives and compute them as functions and store them as .c.h levels.
Okay.
So this PyCalFat becomes a very nice way to integrate with Facefield softwares, particularly when OpenTDB databases are available. So anybody in this community who is a TDB developer, we would like to work with them, particularly for nickel-based alloys, titanium alloys, aluminum alloys, and at least for ternary and quaternary alloys which are of interest. And if you can make such alloys for us, make such TDBs for us, and we will post these open TDBs as part of our software, and we'll utilize them as well. So.
Also, Abhik, I think this is also one unique tool where a phase field simulation is directly talking to the TDB file.
Right.
Most of the tools, so they talk via interfaces provided by softwares, which then internally have something.
Right.
So we are directly talking.
Right.
So I would like to add one more point on top of it. So it is going to be a real application. So for the users who want to work with multi-component alloys, industrially important alloys, so they can directly import the TDB as you mentioned, so without bothering for the information available. So the critical point is here is availability of the data, which can be accessed through any available resources. So
yeah, sometimes industries can pay for the TDB files from respective vendors, and then they can directly work with the code, and so the rest of the community may not have access to those TDB files, but the code is able to deliver things. Right. So that is also a possibility in case it's not publicly available, but available for payment to a particular entity.
Company.
And how about the diffusivity slash mobility values which are available in certain databases that are there, right?
So the same with that. So as long as we can use in principle the same interface for reading in the diffusivity data, because they're just expressions. So the PyCalFat interface, as long as the mobility database is there in a certain format, we can read it and export the diffusivity data in the same way.
Okay.
This PyCalFat thing is a very nice development. It's a substitute for the TQ interface and all of these, things that do not work on expressions, but they have functions for tabulating data. This directly works with symbolic expressions. So that's okay.
Thanks.
Yeah, so Python is open source. Then SymPy is open source symbolic computation, unlike Maple or Mathematica. And so as we learn more and more open source software, we can see how to assemble them together for a solution. So it's like almost like a celebration of open source softwares for scientific research. So the students among the attendees, please pay attention. If you start liking open source software, then you can do a lot more because they're all available for you to assemble as you like.
Particularly SymPy is really, really powerful. You can solve ordinary differential equations in symbolic form just by writing a few lines of code. Coupled differential equations in symbolic form. I mean, it's just opens up several things, particularly for academic purposes. It's very nice. For your courses, you can solve your assignments using SymPy, for example. It's one of the very nice things. Yeah.